Earth Systems 3209. Unit 3, Earth's Materials. Unit 3 references include Chapters 2, Chapter 3, Chapter 6, Chapter 7 in the textbook, and Appendix A and B in the curriculum guides. Unit 3, Topic 1.1. This topic will deal with mineral chemistry. We will focus on outlining a brief overview of mineral chemistry and identifying the elements that make up the Earth's crust. When we look at the building blocks of minerals, to fully understand rocks and minerals, you must first consider the chemistry behind minerals. Things to consider include atoms, ions, compounds, and molecules, and elements. Reference in the textbook can be seen on pages 32 through 38. Let's look at what makes up elements. Elements are made up of atoms, and atoms are the smallest particles of matter. Atoms consist of 5 subatomic particles that are located within the atom. These include the proton. The proton is a positively charged particle located in the nucleus. The neutron, which is a neutral particle, which is also located within the nucleus. The nucleus of the atom is a central portion of the atom that comprises the majority of the mass and also contains the protons and neutrons. Surrounding the nucleus, we have electrons, which are negatively charged particles located in energy levels. And the energy levels are shells that surround the nucleus, which contain or hold the electrons. Atoms are also important in mineral chemistry because atoms can lose or gain electrons to form what's called an ion. And these ions are responsible for forming compounds. An ion is an atom or a molecule which the total number of electrons is not equal to the total number of protons, thus giving the compound or element a net charge, which can be either positive or negative. These positive and negative charges are responsible for combining together to form ionic compounds. So when we look at atoms and ions, both atoms and ions form compounds or molecules, and this is the building blocks of minerals. A compound is a substance that contains 2 or more elements chemically combined. A compound can have properties entirely unlike the elements in which they are made. For example, if we look at halite, halite is made up of sodium and chlorine and is commonly called table salt, which we consume on a daily basis. Salt itself can be eaten, but if we look at the individual components of salt, sodium and chlorine, both are poisonous when they're on their own. So therefore you cannot consume pure sodium or pure chlorine. But when they come together and they chemically bond to form a compound, they form the compound sodium chloride, which is halite. We commonly eat that on a daily basis in the form of salt. Molecule is the smallest part of a compound that still has the properties of that compound. For example, if we look at water, one water drop contains millions of molecules of water. And one molecule of water is made up of 3 atoms, 2 hydrogen atoms and 1 oxygen atom, which are bonded together by covalent bonds. Once we look at atoms and ions, both atoms and ions can bond together in 3 different ways, and they form 3 different types of compounds. These include, number 1, ionic compounds. Ionic compounds involve the ionic bonding between a metal and a nonmetal, where the metal consists of a positive ion and the nonmetal consists of a negative ion. Both the positive ion and negative ion come together where electrons are transferred from the metal to the nonmetal. Once the electron is transferred from metal to nonmetal, this forms what's called an ionic bond, and the compound is now stable. If we look at the diagram below, we see a sodium atom combining with a chlorine atom, and we see one lonely electron in the outer energy level of sodium, which transfers over to chlorine. This transfer of electrons will make the sodium chloride ion stable, where an ionic bond is formed in between. And this ionic bond is a strong bond which keeps the sodium and chlorine closely bonded together to form a compound called sodium chloride, which we commonly call table salt. Text references on ionic compounds can be seen on page 36 and 37 in your text. The second type of compound is called a molecular compound. Molecular compounds involve covalent bonding between two or more nonmetals. When two or more nonmetals come together, the electrons are shared between the nonmetals. For example, in the diagram below, we see two atoms of hydrogen, and hydrogen only has one electron surrounding its nucleus. These two electrons come together as the two hydrogen atoms come closer together, and they are shared between both atoms. Therefore, both atoms now have two electrons that exist in their outer energy levels, and therefore they become stable. Hydrogen gas is stable in nature and is formed by covalent bonding between the two electrons in each hydrogen atom. Text references on covalent bonding can be found on page 37 and 38 in your text. Third type of compound that forms is called metallic compounds. The formation of metallic compounds involve positively charged metal ions existing in a sea of electrons, where the electrons are free to move from atom to atom. Metallic bonds are very strong and is what holds metals together. So if we look at the diagram below, we see a sea of red electrons which move in between all the positive nucleuses of the metal ions. Text references on metallic compounds can be seen on page 38 in your text. Now we know, or we have looked at the chemistry involved in the formation of minerals. Let's look at what makes up a mineral. Minerals are made up of elements, and elements are any materials that are made up of only one type of atoms. There are over 100 known elements, but only 8 of these elements make up more than 98.5% of Earth's crust by mass. It's important to note that the list of these 8 elements goes from most abundant to least abundant. The most abundant element in Earth's crust is oxygen at 46.6%, followed by silicon at 27.7%, aluminum at 8.1%, iron at 5.0%, calcium 3.6%, sodium 2.8%, potassium 2.6%, and finally magnesium at 2.1%. So to review the 8 most common elements located in Earth's crust, we have oxygen, which is most abundant, followed by silicon, which is second most abundant, followed by aluminum, iron, calcium, sodium, potassium, and magnesium. In order to remember the abundance of elements within Earth's crust, we can make a little rhyme, where you take the first letter of each of the elements located in the Earth's crust, and according to the first letters, we can make up a rhyme that would help you remember the order in which these elements exist within Earth's crust. A rhyme that I commonly use would be, overseas American Indians can't swim past Mexico. If we look at the first letter of each of the words in the phrase, it will give you a hint of which element falls in order in abundance within Earth's crust. For example, O in over would stand for oxygen, S in C's would stand for silicon, A would stand for aluminum, I, iron, C, calcium, S, sodium, P, potassium, and M would be magnesium. So some common questions that are posed on past public exams would ask you which are the two most abundant elements found within Earth's crust. So if you remember this rhyme, you would know that over C's would identify the two elements of most importance and higher abundance in Earth's crust. Those would be oxygen and silicon. Another question that commonly is asked on past public exams, it asks you which is the most common rock or mineral group, which is the most common mineral group in Earth's crust. And again, from this rhyme, you know that oxygen and silicon would make up the most common mineral group, which would be silicates. And all silicates would have silicon and oxygen within their chemical makeup. Other materials that make up minerals. Below you'll see the names and symbols of elements found in common minerals. And they include a wide variety of different elements. Some of these elements that make up different minerals include halite, which is made up of sodium and chlorine. Galena is a mineral made up of lead and sulfur. And hematite, which is a mineral that is mined in Labrador City and was mined in the past on Bell Island. So hematite is more commonly called iron ore. It's made up of two elements, iron and oxygen. When we look at a mineral, we should look at the definition of a mineral. So what is a mineral? A mineral is a naturally occurring inorganic solid with a definite chemical composition and molecular structure. Minerals can consist as elements or compounds. The majority of the minerals are found as compounds, such as galena, which is a compound between lead and sulfur, and pyrite, commonly called fool's gold, is a compound made up of iron and sulfur. Minerals can also exist in native form. In other words, they exist as pure elements found in nature. Some native minerals consist of only one type of element. Some of these native minerals include gold, which we find in pure nature, silver, sulfur, diamond, and copper. These are your 5 native minerals which are found in pure elemental form within nature, within rocks, in the Earth's solid ever crust. Note, to be a mineral, a substance must satisfy the 5 following conditions. And these 5 conditions is what makes up the definition of a mineral. A mineral must be naturally occurring, that is, they occur in nature. It must be inorganic. It must be a solid. A mineral must have a definite chemical composition, and it must have a definite molecular structure. So to review, in order for a material to be classified as a mineral, it must occur in nature, be inorganic, exist as a solid, have a definite chemical composition, and have a definite molecular structure. Minerals make up rocks. So a rock is a collection of minerals within the Earth's geosphere, which is the solid Earth. The connection to chemistry is seen as follows. Atoms, which are the smallest building blocks of matter, make up elements, which in turn make up minerals, which in turn will make up rocks. So if we look at the mineral chemistry behind rocks, atoms make up elements, elements make up minerals, and minerals is what make up rocks. Let's look at an example from past public exams. Question number 1 reads, which two elements are most abundant in Earth's continental crust? So if we read the question carefully, it's looking for two elements which are the most abundant in the crust. The rhyme that we remember, overseas American Indians can't swim past Mexico, will outline the 8 most abundant elements in Earth's crust. So if we look at the first two, overseas, that would stand for O, oxygen, S, silicon. So the two most abundant elements are oxygen and silicon that exist in Earth's crust. So the answer to this question will be D, oxygen and silicon. Next question. It says, which of the following is an example of a native mineral? And this question, when we read it carefully, we are looking for a native mineral. And native minerals exist in pure form in nature. Halite would be a compound which is made up of sodium and chlorine. So that would not exist or would not be considered as a native element. Oxygen is a gas, and gases, by definition, cannot be minerals. Ice is made up of hydrogen and oxygen, and again, it's a compound, so therefore it would not be considered as a native mineral, because native minerals are only made up of one element. So our answer in this case will be D, copper. Copper can exist within rock in pure elemental form, so it's called a native mineral. Example 2. The questions read, which consists of at least 2 elements? If a material exists of 2 elements, it would exist as a compound or a molecule. And in this case, our answer would be B, compounds. Second question reads, which type of bonding between atoms displays the sharing of electrons? So if we read this question carefully, we look at the bonding between atoms by sharing electrons. Sharing electrons is an example of covalent bonding, whereas if it was transferring of electrons, it would be ionic bonding. So our answer to this question would be A, covalent. Your turn. Take the time to complete the following question. These questions can be prepared and the solutions will follow on the next slide. So you stop your recording now to analyze the questions and prepare your answers. Let's review the questions. Which factors indicates whether a substance is a mineral? So here we're looking at which factor would identify a substance as a mineral. According to the definition, a mineral must be naturally occurring, inorganic, a solid, have a definite chemical composition, and have a definite molecular structure. So when we look at our choices, C would be the answer. Form naturally. So all minerals form in nature, therefore they form naturally. Second question. Which of the following statements are correct? These statements deal with the chemistry behind rocks. And we've learned that the smallest particles of chemistry will be the atoms. Atoms make up elements, elements make up minerals, and minerals make up rocks. So in this case, our answer would be D. So again, when you look at your 4 choices, we could eliminate 2 of the choices because we know that atoms are the smallest particles of matter. So therefore, minerals could be eliminated as the smallest particles of matter, or the beginning of this sequence. And if we look at the last words present, we know that rocks will be the final end. So we're looking for rocks at the end, atoms at the beginning, and therefore D would be your answer. Atoms make up elements, which make up minerals, which make up rocks. So the solutions are as follows. A mineral is a substance that is formed naturally, and if we look at the sequence, atoms make up elements, make up minerals, which make up rocks, would be the correct answer. In summary, rocks are collections of minerals, which make up Earth's solid earth. To be a mineral, a substance must satisfy 5 conditions. It must occur in nature, it must be inorganic, it must be a solid, it must have a definite chemical composition, and it must have a definite molecular structure. So these 5 characteristics is what defines any material as a mineral. And when we look at rock chemistry, we know that the smallest particles of matter are atoms, which in turn make up elements, which in turn make up minerals, and finally, minerals make up rocks.